Hello and welcome to another video. In this video we're going to be working on a number of possible sets of closing branches from the Biweekly Contest 119. It's going to be the hard problem for that one. And in this problem you have a company with n branches across the country, some of which are connected. Initially you can reach any branch from any other branch, and we're given an integer n, which is all the nodes, max distance, which is the max distance you can have once some branches close, and rows, which are all the edges and the edge length. And we're asked to return all sets of branches that we can close, such that if we close a branch, every other branch that's not closed can still visit every other one, and the max distance from any one of them to any other one is this number here. So let's see kind of what they mean. So they show that if we close, for example, node 2, so if we close node 2, then any road that goes to node 2 is no longer there. So this one's no longer there, this one is no longer there. And now the only nodes left are 0 and 1. And to get from 0 to 1 is 2, so that's fine. Also, there is another set that we can close. We can close 0, 1. So if we close 0, 1, all the roads are gone now. So obviously, whenever you have one branch that's open, it's always going to be fine because you can get from one branch to itself in 0. So you're always going to be able to get max distance. So 0, 1 is fine. 1, 2 is fine. 0, 2 is fine because we'll only have one open branch. And also we can close every single branch. That's always going to work because if we close every single branch, then there are no branches, so you can get from every branch to every other branch. Now let's look at the next example. So here we have this example of multiple roads from one node to another. And they said that which sets can we close? So we can close nothing. That's a viable set because let's take a look. So from 2 we can get to 0, length 2. We can get to 1, length 2. And from 1 we can get to 2, and we can also get to 1 like this, or from 1 we can get to 0 like this, right? So you can just take this path to go from every node to any other node in under 5. So here basically you can close nothing, you can close, also if you close 0, then this road is gone and this road is gone. So this is still fine. Then let's take a look at some other stuff. We can close set 1 as well. So if we close that one, this is gone, this is gone, this is gone, and now we can go here. So notice they say we can't close set 2, so let's see what happens if we close set 2. So if we close set 2, any road with set 2 will be gone, and now you can't get from 0 to 1 in 5, right? It takes too far. So we can also, obviously, once again, we can close sets of branches where there's only one open branch, and we can close every single branch. So this is going to work with any graph you have. So in the third example, we have one branch, max distance is 10, there are no roads. But obviously, like I said, we can close no branches because it will have one open branch, which should always work. And we can close every branch, so we can write that down. So things that always work: close all branches and close all but one branch, right? Because if we close all of them, then obviously you'll be able to get from everywhere to everywhere because there will be nothing. And if we close all but one, the distance from a branch to itself is 0, so it's always going to get into max distance. So I actually didn't write the constraints here, but the constraint is n equals 10. And because of that, this is one of those problems that you really need to be looking at constraints, because since n equals 10 and roads is actually 1,000, I believe, and then the other stuff doesn't really matter. So n equals 10, roads is 1,000. So if you think about it, how many total sets can we make, right? And total sets of branches we close, like for example, let's take a look at this first one, right? If we have like 1 and 2 and 3, what are sets of branches we can close? Well, we can close nothing. So maybe like the empty set. We can close 1. We can close 2. We can close 3. We can close 1, 2, 1, 3, 2, 3, and 1, 2, 3. So notice we can close, like, the way this works. How do we represent all of these sets in some kind of, like, how do we quickly figure out like what set we're in? So when they ask you this question, like represent every single set or every single state of, you have a bunch of things and there's not too many of them, right? Like, what does this sound like? I have a small amount of items they can only be on or off. I want to represent states with combinations of this. So this is a perfect scenario for a bit mask, right? So essentially we can represent all of these sets with a bit mask, where if we have, let's say, n nodes, let's say it's like 3, we can just have a bit mask of 3 nodes, you know, like 0, 0, 0 will mean you can represent it however you want. 0 might mean open, 0 might mean closed. In my case, 0 will be closed and 1 will be open. So this means like everything is closed. This means everything is open, and I can have any other state, right? So this is going to be the 0 node, the 1 node, the 2 node. I'm going to go right to left, total preference there. But now essentially what we can do is we can just have a bit mask for these. And so what's the biggest number and the smallest number we can have? So if n equals 3, and I'm going to represent 1 as open, so I'm going to write that down. 1 is open, 2 is closed, and index will go from right to left, right? So like this will actually be node 0, node 1, node 2. So the range we can represent, if n equals 3, the biggest number is this, and the smallest number is this, and this is always going to be the case. So if n equals something, we have x ones, right? Like if n is 10, then we would have 10 ones or zeros. So this is going to be the biggest number, and then the smallest number is just x zeros. So what's the range here? Well, this is a common problem. I don't know if you've seen it before, but this is a very common problem. This is just 2 to the n minus 1, right? So 2 cubed here would be 1, 0, 0, 0. So this has 4 bits, subtract 1, and now we get the bits we want. So the range is going to be 0 to this, to 2 to the n minus 1, right? These are like the different bits we can have. And then we just have to check all of these. So in my case, if 1 is open, then I'll just check, like I'll have some state. So let's say my state is like 1, 0, 1. That means that, you know, branch number 1 is closed and these other ones are open. And then I have to simply check for this configuration, is this possible? So now let's talk about that. Let's say we have some configuration and we want to figure out, is this possible? And the way we can do this is we can actually copy this example. So let's do that. Bring it down here. And let's say, for example, let's start off with like, we close no branches. So they're all open. So what we really want to do is we want to have a couple things. One, we want to have a set of all branches in the mask, right? Because these are the branches that are in our bank, like that are in our current set of open branches. So we want to figure out like what are all the branches in our mask that are open. So we can write that down. And remember, we can just loop from 0 to the mask and figure out like for all of these states, are they viable? And if they are viable, we'll add 1 to our set of things we can close, right? So for example, if we have something like this, if this works, if we are able to have this and we can have a path from every node to every other node that matches all this criteria, then this will be a state that can be closed, right? And this will be symbolized as 2 is open, 1 is closed, and 0 is open, so that'll be a state of like 1 being closed, and so on, right? But we don't really care about like what the mask correlates to in a set. We just have to count them up. So let's say we get a mask, and the mask is like this. So our nodes here, because these are all on, first we want to go through the mask and figure out what nodes are all on. That's pretty straightforward. You can just loop 1 to n and just AND it with a 1 in the right position. So let's say we want to check like if node 0 is on, we can just AND it here, right? We can AND check for node 0, this will be 1 or 0, and so on. And we can just loop through all of the bit mask, because the bit mask is only like 10 nodes. So now that we get our set of nodes that are on or open, so let's say we have 1, 2, 3. Now we have to figure out how to build adjacency lists efficiently. Then this is like one of the biggest parts of this problem. So to build an adjacency list efficiently, like I said, this roads can be 1,000, and this nodes is only 10. So what's going to happen here is you're going to have a ton of duplicate roads. You can have like 10, 20, 50, and so on, right? And the main thing to recognize is when we're looking for shortest paths, if we have duplicate paths, like let's say we have this path, and this path, well, what path are we gonna use and what path will we never use? Like if all these nodes are on, let's say, we're never going to use this path. We're never going to use this path. We're always going to use the shortest path. So when we populate, what we're going to do is we're going to populate a hash map and our format for a hash map. So you can do this a few ways. I think most people did the Floyd-Warshall. I'm just going to do a normal Dijkstra's, and Dijkstra's is pretty good here. And I think the time complexity for Dijkstra's, worst case scenario, is like v cubed log v if edges approaches v, but we're also going to have like a bunch of things that we can terminate early on. Since v is only 10, like this is basically the same. So I'm not a huge fan of like learning new algorithms for like 1 or 2 problems. So I have seen how to do Floyd-Warshall, but I barely use it. So I'm just gonna do it with Dijkstra's, and it should be fine. Because our constraints are so small, right? N is only 10, so 2 to the 10th. This is all the possible sets we can have. This is like 1,000. And then v cubed is 10 cubed, right? So it's also 1,000. So it's like 1,000 times 1,000, but we'll also have a bunch of early terminating conditions with Dijkstra's, which will in reality make it significantly faster. So now that we know, like, we want to always just store the shortest edge, the format we're going to have, so normally in an adjacency list, you have a format of like, you have a key, and then you have a list of edges, right? Normally, like a key will be node list of edges. We're going to do something a little bit different. I don't know if I've used this before, but I just found this really useful for this problem. So instead of having a key for a list of edges, we're actually going to have a dictionary of dictionaries of integers. And so, for example, the dictionary originally will be like the node that the edge is coming from. So let's say if we have an edge from 0 to 1, it'll be like 0 will go to 1, and then that path length will be 10. And that's how we're going to store it. So, and then also obviously we'll have the other way around. So we'll have 1, we'll go to 0, we'll have like this. That way we can look up these, like if we want to check 0 to 1, we can look it up in O of 1. We don't want a whole list. We want to be able to find this list quickly, right? Or this like edge quickly. So that's what we're going to do. So instead of having an dictionary of lists, we'll just have a dictionary of dictionaries, but pretty straightforward. So first let's populate this dictionary and let's kind of see what's going to happen here. So let's say this 0 first, like we go through the road. So let's say, so 0 to 1 has 20. So we're going to say, okay, 0 to 1. So remember it's dictionary, and so it's going to be like this, 20. Then obviously we want to have the reverse. So 1 to 0 will be also 20. Now 0 to 1 has 10. And when we go to 0 to 1, we're going to check, is there a value here? And if there is a value here, we're just going to replace it by the smallest value. Because when we look for shortest path, why would we take a longer path? That doesn't make any sense. So we don't need to store all of these roads. If it's like 1,000 roads, we can just store 10, or not 10, it'll be like 100 edges max. But it's going to be a lot more efficient for traversal, because also keep in mind, we're in a lot of these cases, most of our nodes are going to be, or a lot of these nodes are going to be off. So we're going to store in reality way less edges. So if there's like a ton of duplicate edges, let's say on average there's 10 duplicate edges, we'll only store one of them. So that's going to make it a lot faster. So here we're going to replace 20 with 10, because this is, remember, we're always going to store the shortest edge. Then we keep going. So 1, 2 has 2. So we're going to say 1, 2 has 2, and also the reverse, right? Because it's unweighted. And then 0, 2 has 2, and the reverse. Okay. So now what we need to do, now that we have this stored, we can do a couple things. We can have a couple like early terminations. So for one thing, what we can do is we can say if the number of nodes is less than or equal to 1, right, in our graph, we can just return true, because this will always work. If we have 1 node or 0 nodes, we don't need to do this whole list building stuff. There's no point. Like if you have 1 node, it can only go to itself. And if you have no nodes, it'll always be fine. So that's one early termination. That's going to save us a lot, because we don't need to look through 1,000 roads for no reason. Now, another early termination is if we have more than 1 node and our list, our dictionary list, so if length of dict is less than the number of nodes, that means that there are some nodes, so we have more than 1 node, and there are some nodes that don't have any edges coming out of them. So if there are some nodes that don't have any edges coming out of them, then obviously it doesn't have any connection, so we'll just have like a node all by itself, and this will also never pass, right? So these are our 2 early terminations. This is going to be return false here, right? because that means we'll have like some node like this that's by itself, and then we'll have some other nodes that are connected. So if there's a node that's by itself that has no edges, how can we possibly get to it or from it? We can't. So those are going to be early terminations. We'll have a couple other ones. So now what we really need to do is just do the normal Dijkstra's. So normally for Dijkstra's, what happens is we are trying to find the shortest path from A to B, right? And the way it works is we have a heap. So I'm going to assume you know Dijkstra's if you're doing problems like this. You have a heap, and then you are just keeping track of like your paths and your visited nodes and so on. And then once you get to B, you're guaranteed to get there the fastest way. Well, we can easily modify Dijkstra's. Instead of going from A to B, we can say shortest path from A to all other nodes. And it's a very small modification. All we say is instead of just getting to B, we'll just keep going. We'll just keep traversing until we visit every node. So we'll have a visited set and keep going while we have a heap and visited set is less than total nodes, right? So it's very easy. We just keep traversing. Anytime we visit a node, we put in the visited set, and we keep going while we have a heap of edges, and until the length of the visited set is actually less than the total nodes, because we have to go from one node to all nodes. So for example, let's see, let's kind of do this one. So let's say we start at node 0, and we're trying to get to every single node. So yeah, let's actually redraw this a little bit lower. So we're gonna have like 0, 1, 2, and let's take a look at the distances. So we have 2, 2, 10. So 10, 2, 2. So like normal Dijkstra's, you're gonna put in 0. So you're gonna store two things, right? You're gonna store the path length and the node. So it'll be like 0, 0. And what's gonna happen here is we are going to pop the 0, 0. So we're going to pop the node and the distance. So remember, distance first, node second. We're going to pop the node and the distance. We're going to have a visited set. We're going to say we haven't visited it yet, so let's add it to the visited set. And also check, once we get to a node, this is going to be our other early termination. We're going to have like the shortest path to it. So if it's not visited, so if not visited, and distance is greater than that max length or max path, also return false, right? Because we got to it the shortest way we could, and it's too long. So that's going to be our other early termination. For 0, we're fine because it's just 0 to itself, so we visited 0. Now, obviously, we go to the neighbors and we check where do we want to go. If you want, I guess what you could do is you could have another case. I don't think I added this in my code. So when you add a path, like let's say this path is 10, you technically don't even need to add it. I guess another way you could save like some more optimizations I'm thinking of right off the bat that I didn't even add is actually when we populate the list of edges, anytime we have an edge greater than the max path, right, we can just not use it. So that would be another way to do it, right? So whenever we have these edges, if it's greater than max path, no point. And also, yeah, so that could be something we could do. So that's like another optimization you can make, because it's never going to work, right? So any edge greater than max path, I guess I'll add that to my code as well. It's like one line of code. So yeah, that's going to be another one. So essentially we visit 0. Now we check for all of its parents. So let's actually do that. Let's actually pretend this doesn't exist now, because this shouldn't exist, because it's totally useless, because our max distance is 5. So now we check what are the paths from 0, and this is going to be 2. So we're going to check, have we visited 2 yet? No, we haven't. And is the path length fine? Yes, it is. So what we're going to do is we're going to add a path of 2 and a node of 2 to our min heap. And then that's going to be our min heap. There are no other neighbors. So then we pop this 2. We check, have we visited yet? No, we haven't. Is the max path bigger than 5? No, it's not. Add 2 to visited. And then what are the neighbors of 2? It's this one over here, the 1. So once again, we add the path, the total path. So it was 2 before, plus this 2 here, so it's going to be 4. And now we visit 1. And now this is our heap. So we pop again, and we have 1. And our path length is 4, so we add 1 to visited because the path length is 4, it's less than 5. So this is totally fine, right? So from 0, we were able to visit everything. Then you do the exact same thing from 2. So you just clear your visited set, do the exact same thing from 2, it'll work, and do the exact same thing from 1, it'll work as well. And if any one of these fails, or you have any one of these like 5 early terminations, then this fails. And basically that's kind of all you need. So you just do this, you just have a helper function that does this, you build up all of your nodes, you make sure all of these things pass, and your time complexity will be something like, for each case of Dijkstra's, is something like v cubed log v, like I said. Log v, and this log 10, so v cubed's like 1,000, and all of your unique sets are 2 to the 10th, which is also like 1024. So totally fine. So you'll be like 1,000 times 1,000, 10 to the 6th. And with all these early terminations, this is going to run super fast, easily pass. I actually looked at my code. I think I was getting like in the 200s of something of time, and most people's code was like 4,000 ms with the Floyd Warshall. So it's like 20 times faster. And I still didn't add this other edge thing that we could add right now as well. So let's see if how much that speeds it up. Yeah, so now we're going to look at the code. I didn't want to code it up. I didn't want to code it up as we go because I don't want to make this video too long, and it's kind of long, so let's go over it. So we have this check path, which will take a bit mask, and it's going to build this up like I was saying. So we have nodes, and basically for every single, we just loop through the bit mask, and for every single different bit, we check if it's a 1, and if it's a 1, we set the corresponding node into the nodes, right? And then we can, so this node is going to contain all of the nodes that actually have connections. Then, like I said, if there's only one node or less, then we can return true, because if there's one node or less that's on, that's always going to work. Then we build an edges hash map, and like I said, the way it's going to work is we're going to have start and distance, and we're going to have a dictionary of dictionaries of ints. So as you can see here, in edges start, you build another dictionary, and then you add an integer here. And this is just going to populate it. So let's add that other thing. Let's see where that's going to go. I think we're going to add that here. So if distance is less than max distance, we can continue. So, or if distance is, or dist is greater than max distance, because that's going to be completely useless. We never need that. There we go. So small little line there. So now we have this dictionary of dictionaries. And like I said, if you have more than 2 nodes and there are no edges for one of them, this will never work because you'll just have an unconnected vertex that you can't get to from anywhere else. So early termination there. Then we have this little termination. We also have this termination. And now this is just normal Dijkstra's, right? So we just loop through every single node and we basically run Dijkstra's on it. So we have a visited set. We have a heap with the node itself with a path length of 0. And we just do normal Dijkstra's. So yeah, this is just normal Dijkstra's. Also, if we ever get a distance, like I said, if we have a node that hasn't been visited and distance is greater than max distance, then that means that this is the shortest path to that node from our starting node, and it's too big, so this is going to be false. Add it to the visit set, and then check all of its neighbors. If they're not in visited, then add this thing. You could also... Yeah, so I guess we could add that as well. So we could only add edges here that are only good. So we could say like if distance, this thing right here, if distance, if this is less than or equal to max distance, we can do it. Otherwise, we don't need to. So less than or equal to max distance. I think that should... This one, I'm not sure if it'll speed it up because we're doing this a bunch. We'll kind of check both ways. Yeah. So if the edge is too long, no need. But otherwise, let's add it. Okay. And then finally, at the end, if your visited set isn't entirely full and your heap is empty, that means you didn't visit all your nodes, and you can return false. So just because nodes have edges doesn't mean they will you'll be able to visit every node from any other node. Like let's say nodes 0 to 1 are connected and nodes 2 to 3 are connected. There's still no connection from like one of these to another one of these, right? So this will never work. Yeah, and if we are able to do that for every single node, then we just return true. Then we have our result. We have the bit mask from 0 to 2 to the n-1, because this is non-inclusive. And then we just literally put in the state, check the path, and return it. And let's see if our optimizations helped or didn't. Let's take a look. What issue we have. Valid syntax. Or if distance Let's see. Oh, right, we don't need that. If. All right. So I think this is about the same. Let's get rid of this one because I don't know if this one helps. I know the other one helps for sure, but I don't know if this one does. Actually, maybe the other one, I'm not sure either. But let's see. That's about the same. Yeah, okay. So either way, so these ones aren't that big. But yeah, you can see it's like 200 ms. I think before it was like 300 ms. So I guess we'll leave it if it's the same. Whatever. Yeah, but like I said, very, very fast compared to most other ones. Most other ones I've seen were like 4,000 with the Floyd Warshall. So this is like, if 4,000 passes, this easily passes, not even close. So no point really learning a new algorithm to do this. You can just do this with regular Dijkstras. It's just a lot more coding. I think Floyd Warshall is more convenient because you basically do like a triple loop, and it's just more convenient where this one's a little bit more code. But still not too bad. So the biggest thing is, like I said, check the constraints, realize the constraints are small enough to just brute force this, and yeah, and then you don't have to go do anything tricky. So as long as you figure out like how do I represent every set, bit mask, that's going to do it. That's going to happen a lot when you want to represent every set or some kind of thing. That's like not super common, but common enough where I have seen it before. If you want to represent every state possible where you have a bunch of like on-offs, bit mask, definitely the way to go there. Yeah, and I think let's talk about the time for this one. So like I said, Dijkstra's is roughly v cubed, because it's like v, and then it's like, I always get this wrong. I think it's like v plus e or something, like log v, or maybe it's like this, or yeah, I always get it wrong. Anyway, I think for one node it's around v squared, and so for 3 nodes it's it's like v squared log v for one node. And for all nodes it's going to be v cubed because you do it for every node, and yeah, log v here, but because v is only 10, like this is basically nothing, so it's going to be like log, this is going to be for one iteration, and then we have to do this for every single bit mask. So this is going to be from it's going to be something like this, right, from 0 to the end. So this is like the overall time complexity, and the space. So what do we have here? We do build up this like dictionary of dictionaries, but it's going to be the same space as building up a list, like a dictionary of lists, visited nodes, and all that stuff. That's basically nothing. Dictionary of dictionaries is going to be something like v squared, right? Like if every node has an edge to every other node. Remember, we're not storing duplicate edges. That's why we're saving a lot here, right? Like if we have 2 edges, we realize we just want the shortest one. The bigger one's always going to be redundant. So I think it's going to be something like this. I never get it right with Dijkstra's because like everyone has different times and spaces. So let me know if I screwed something up there. But yeah, I think that's going to be mostly that. And I did actually finish the normal contest for this week. I'm just going to make videos for it, so I'll do that in the next couple days. These two are actually quite easy compared to the normal ones. Like the hard problem, or not the hard problem, like the third problem for both of them was really easy compared to the average one. So, and also the hard problem is also, like, this one's not too bad. The other one was also not too bad compared to some crazy ones that I've seen before. So I'll definitely be making those soon. Hopefully you enjoyed this one. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.